This line of code is intended to be executed in a command line environment, such as a terminal or a shell, to automatically install Python packages listed in a file called requirements.txt. It uses Python's pip package manager to manage the installation of packages. The first part, import sys, is a bit misleading because it looks like a Python command but is not used in a standard Python script here. Instead, the symbol is commonly used in environments like Jupyter Notebooks to execute shell commands from within the notebook cells. The sys.executable dynamically refers to the path of the Python interpreter that is currently running the script, ensuring that the correct Python instance is used for installing the packages. The M flag stands for module and tells Python to run a library module as a script, allowing you to run a module's functionality as a command line utility. Pip is Python's package installer. The install command tells pip to install something. Our requirements.txt specifies that pip should install all the packages listed in the file requirements.txt. This text file contains a list of Python packages with possible versions specified, which are necessary for a particular Python project or environment to run correctly. In summary, this code facilitates an easy and automatic way to set up a Python environment with the specific packages and versions needed for a project. The code block you've given is a series of import statements in Python which are used to bring specific libraries or modules into the current script, allowing the use of their functionalities. Here's what each import does. 1. Import scipy. This imports the scipy library, a collection of mathematical algorithms and convenience functions built on the NumPy extension for Python. It adds significant power to the interactive Python session by providing the user with high-level commands and classes for manipulating and visualizing data. 2. Import patsy. This imports the patsy library, which is used for describing statistical models and building design matrices. 3. Import pickle. This imports the pickle module, which is used for serializing and deserializing Python object structures, also called marshalling or flattening. 4. Import numpy as np. This imports the NumPy library with the alias np, which is a fundamental package for scientific computing in Python. 5. Import pandas as pd. This imports the pandas library with the alias pd, which provides data structures and data analysis tools for Python. 6. Import scipy.sparse. This specifically imports the sparse matrix functionality from scipy, which is useful when working with matrices that contain a lot of zeros. 7. Import matplotlib.pyplot as plt. This imports the pyplot interface from the matplotlib library with the alias plt, which is used for creating static, interactive, and animated plots in Python. 8. From statistics. Import median. This imports the median function from the statistics module, which is a built-in Python library for simple statistical calculations. 9. From scipy.stats import Gaussian_KDE. This imports the Gaussian_KDE class from the stats submodule of scipy, which is used for kernel density estimation with Gaussian kernels. 10. From statsmodels.formula.api import ols. This imports the ols function from the stats models library, which is used for ordinary least squares regression. 11. From tqdm import tudm. This imports the tqdm module, which is a tool for creating progress bars that can give feedback during loops. Meta explanation. The purpose of these imports is to load various statistical, numerical, and plotting capabilities into the Python environment, so the programmer can work with data structures, conduct statistical analyses, serialize objects, perform matrix operations, and create visualizations. The specific tasks the script will perform depend on the subsequent code, but with these imports, it likely involves data manipulation, statistical modeling, and generating graphical outputs. The code is used to load serialized data from pickle files located within a particular directory structure and update dictionaries with the contents of these files. Specifically, it is designed to load and aggregate data for different years into 3 separate dictionaries: data, covariance, and daily_return. The first part of the code initializes an empty dictionary named data and loads a pickle file named pandasframes.2004.pickle from a directory denoted by bar_dir. It then updates the data dictionary with the contents of the pickle file. The second part initializes an empty dictionary named covariance and loads pickle files corresponding to the years 2003 and 2004 with file name structured as covariance year.pickle. Each file's contents are added to the covariance dictionary, sequentially updating it. Finally, the third part creates an empty dictionary named daily_return and loads pickle files for the years 2004 and 2005 with file names in the form of price year.pickle. It updates the daily_return dictionary with the data from these files. Overall, the code is aggregating potentially different datasets across multiple years into structured dictionaries for easy access to the contained data after it has been deserialized from the pickle files. This code appears to be part of a larger Python script that processes financial data. Specifically, it aims to merge datasets from 2 different sources or types of financial data based on their dates, with a specified delay between them. The variable frames is initialized as an empty dictionary. It seems like it will be used to store the resulting merged data frames, keyed by the price_date. The delay_n_days_delay is set to 2, which appears to specify the delay in days between the 2 data sources when merging their corresponding data. Within the code, date_shifts is created using the zip function, which pairs elements from two iterables together. These iterables are the sorted keys of the data and daily_return dictionaries, with the keys of the latter being offset by _return_in_days_delay days. This offset is achieved by slicing the sorted keys of daily_return to start at the index given by return_in_days_delay into inline data, plus return_in_days_delay positions later. A for loop then iterates over these paired dates, date_date, price_date. For each pair, a new data frame is created by merging the data frame from data_date, with the data frame from daily_return price_date, based on the borrowed column common to both data frames. The merged data frame is then stored in the frames dictionary, using price_date as the key. The overall effect of this script segment is to produce a set of merged data frames that correspond to financial data from two different data sets matched by date with a defined delay, which could be useful for financial analysis or backtesting trading strategies that require aligning data points with a time shift. The purpose of this Python code snippet is to iterate over a dictionary named frames where each key value pair consists of a string daily return date matched with a data frame, df. For each data frame in frames, it first calculates the number of rows in that data frame by df.shape 0. Then, it creates a new column in the data frame named daily return date and fills this column with the key string, which is daily return date in this context, repeated for as many times as there are rows in the data frame. Essentially, the code is used to add a new column to each data frame within the dictionary that contains a constant value corresponding to the key associated with that particular data frame. The PD series is used to create a new series object that will be assigned to the new column. The code is accessing a data frame that is likely stored within a dictionary called frames using the key 200400108, which appears to represent a date string formatted as YYYYMMDD. After retrieving the data frame associated with this key, the .head method is called on the data frame. The purpose of the .head method is to return the first few rows of the data frame for quick inspection. By default, it returns the first 5 rows. This is often used to get a glimpse of the data structure, including the column names and the type of data that each column contains. The code is used for displaying a snippet of the data frame content related to the specified date without printing the entire set of data, which can be helpful for large data frames. This function wins is designed to apply a winnowing or clipping effect to the input array X with respect to the boundary values A and B. Specifically, it takes each element of X and performs the following checks. If the element is less than or equal to A, it is replaced with A. If the element is greater than or equal to B, it is replaced with B. If the element is between A and B, it remains unchanged. The function relies on the np.where function from the NumPy library to perform these operations, which returns an array with elements chosen from either A, B, or X based on the specified conditions. The purpose of this code is to ensure that all elements in the resulting array fall within the closed interval A, B. This type of operation is common in data processing where it is necessary to limit or clip values to a specified range. This Python code defines a function density_plot for visualizing the density distribution of a dataset using Gaussian kernel density estimation. The function takes one argument, data, which is the set of values to be plotted. Inside the function, a Gaussian kernel density estimate KDE object is created from the input data, which estimates the probability density function of the dataset. The data is then used to compute a range of X values evenly spaced along the range of the input data using NumPy's linspace function, which is stored in the variable XS. The covariance_factor of the KDE is manually set to 0.25, which influences the smoothness of the density estimation. After setting this factor, the code computes the covariance of the KDE. The density estimation is plotted against the XS values using matplotlib, as indicated by the PLT alias, producing a line plot of the density function. The plot is then labeled with daily returns as the x-axis label and density as the y-axis label before being shown. After defining the function, the rest of the code performs an operation on a selected subset of data from frames, indexed by the date 200400108. It applies a winsorization process via the wins function, which is not defined in this snippet, to the daily return column of the subset to limit its extreme values, and then plots the density of the winsorized daily returns using the density_plot function defined earlier. This winsorization step ensures the extreme values do not heavily skew the resulting density plot. The provided code is a set of Python functions that are likely part of a larger module designed to estimate financial factor returns using linear regression on a dataset of securities. 1. Get_formula function constructs a formula string for a statistical model, specifically for use with the OLS, ordinary least squares, function, which is used for linear regression. The string is built by linking a dependent variable y, which represents the returns, e.g., daily returns, with a set of independent variables factors, which represent financial factors. The resultant formula string resembles a typical linear model equation like y0 plus factor 1 plus factor 2 plus, which is usable by the regression modeling function. 2. Factors underscore from underscore names function filters a given list of names to only include those that contain the substring usfasted underscore, indicating that they are a certain type of financial factors. 3. Estimate underscore factor underscore returns function estimates factor returns from a data frame DF. It performs a series of steps to prepare the data, which includes filtering the data frame to include only securities with a market capitalization greater than $1 billion, creating a universe of large cap stocks. Applying a winsorization process to the daily returns by limiting the extreme values to a specific percentile range to mitigate the impact of outliers during model fitting. Extracting the relevant factor names from the data frame columns. Building a formula string based on these factors and the daily returns. Fitting an ordinary least squares regression model to this prepared data to estimate the relationship between the factors and returns. The function then returns the results of the model fitting, which include the estimated coefficients and statistics for the factor returns. This code does not execute the functions but defines them for later use, presumably to be part of a larger analysis pipeline in financial analysis for factor investing or risk model construction. This code snippet appears to be iterating over a collection named frames, where each element in frames is associated with a date. It creates an empty dictionary named facret, which is intended to store factor return estimates for each date. For each date in frames, the code calls a function estimate underscore factor underscore returns, with frames, date, as the argument. This function likely performs some sort of statistical analysis or modeling on the provided data to estimate factor returns, which are associated with financial investments. The .params property of the result suggests the function returns an object with parameters of the estimated model. The estimated factor returns for each date are then stored in the facret dictionary with the date as the key. Thus, after the loop executes, facret contains a mapping of dates to their corresponding estimated factor returns. This structure could then be used for further analysis, such as portfolio optimization, risk assessment, or performance attribution. The code snippet takes a dictionary called frames where the keys represent dates in the format YYYYMMDD, converts these date strings into datetime objects using pandas to underscore datetime function, and then creates a list of these datetime objects. The purpose of the lambda function is to serve as an anonymous function that takes each key, date string, as an argument and applies PD to underscore datetime with a specified format, %y% and %d. For converting string to datetime object, the map function applies this lambda to each key in the frames dictionary. The list function then converts the map object into a list of datetime objects. Finally, the sorted function sorts the list of datetime objects in ascending order. The result, my_dates, is a sorted list of datetime objects corresponding to the original date strings in the keys of frames. This piece of code is designed to create and plot the cumulative returns of different financial factors over time using Python's pandas and matplotlib libraries. The alpha_factors variable is a list that contains the names of the financial factors of interest. My_dates is assumed to be an iterable that contains date objects, although its definition isn't provided in the code snippet. A pandas data frame facret_df is initialized with an index corresponding to the my_dates. The code then iterates through each date and my_dates in each factor name and alpha_factors. For each combination of date and factor, it locates the corresponding return value in some external data structure, presumably denoted by facret, indexed by a string representation of the date and the factor name. This return value is then assigned to the appropriate cell in the data frame, facret_df. After populating facret_df with the factor return data for each date, the script iterates through each column, each factor, in the data frame. It plots the cumulative sum, which represents the cumulative return over time, of the returns for each factor as a separate line on a graph. A legend that identifies each line is placed in the upper left corner. Acts as labels for the date, and cumulative returns, cumulative factor returns, are set. Finally, the plot is displayed using plt.show. Essentially, the code is used to visualize how each financial factor's returns accumulate over the set of dates provided, thereby providing an overview of the factor's performance over time. The code defines a function clean_nas that takes a data frame df as input. Within this function, it first identifies numeric columns in the data frame by selecting columns with data types that are numerical, using number pysnp.number. The column names for these numeric columns are stored in a list called numeric_columns. After identifying the numeric columns, the function iterates over each of these columns and replaces any nan, not a number, values with a numerical value, defaulting to 0, using the np.nan_to_number method. The np.nan_to_number method is applied directly to each column, thus modifying the data frame in place. Finally, the function returns the modified data frame, which now has nan values in numeric columns replaced by 0. This cleaning is commonly done to avoid errors in mathematical computations, as nan values can cause issues with various algorithms and operations. The purpose of this code is to perform a data manipulation process using pandas, a data analysis library in Python. Initially, a data frame called previous_holdings is created with 1 row and 2 columns, barred with a value of USA02P1, and h.op previous with a numeric value of 0. Next, the code selects a data frame indexed by the date format %y%m%d from a dictionary or a list of data frames named frames. This selected data frame is stored in the variable df. The df data frame is then merged with the previous _holdings data frame on the borrowed column using a left join, meaning all rows from df will be kept, and matching data from previous _holdings will be added where available. After merging, the clean_nas function is called on df, which is likely a custom function intended to clean the data frame by handling any NaN, not a number, or missing values resulted from the merge operation. Finally, the code attempts to set the spec risk column values to the median of the spec risk column for the rows in df where spec risk is equal to 0. However, there seems to be a mistake in the code. The expression df.lock, df spec risk equals 0 spec risk intends to filter out the data frame rows where spec risk is 0, and the assignment operation intends to replace the 0 values with the median of the spec risk column. However, this line of code will not have any effect since it does not assign the result back to df. To correctly modify df, the code has to be written as df.lock, df spec risk equals 0 spec risk equals median df spec risk. Please note that median in this context is not a predefined function, so it is assumed to be a custom function or should refer to numpy.median or pandas.dataframe.median, and it needs to be called with the right namespace or imported properly to work. This code defines a function get_universe, df, that takes a data frame df, which is assumed to contain stock data. The function filters the stock data to create a subset, a universe, of stocks that meet certain criteria, those that have an issuer market cap of greater than or equal to 1 billion, 1 times 10 to the power of 9, or stocks for which the absolute value of the h.op previous is greater than 0. After applying the initial filter with .lock, the function proceeds to copy the resulting data frame to avoid any setting with copy warning that may arise when modifying a slice of the original data frame. Next, it drops the daily return column from this filtered data frame, most likely because this column is not required in the resulting universe. Once the specified column is dropped, the function returns the reduced data frame, which is the final universe of selected stocks. At the end of the code snippet, the get_universe function is called with df as the argument, and its return value, the filtered universe of stocks, is assigned to the variable universe. This line of code is intended to retrieve a date from the universe dictionary or data frame, convert it to an integer, and then to a string. More specifically, it accesses the date key or column within universe, then takes the second element, index 1, assuming 0-based indexing, likely representing a date in some numeric format. It casts this value to an integer, which could be a process to ensure that any leading zeros are removed or to convert a floating point representation to a whole number. Finally, it converts this integer back to a string, potentially for formatting or displaying purposes. This operation is especially useful if date held dates in a non-string format, and there is a need to manipulate or use them as strings in subsequent operations. The purpose of this line of code is to generate a list of factors using a function named factors_from_names by passing it a list of names taken from a variable called universe. The factors_from_names function presumably takes a list of names and returns their corresponding factors, although the specifics of what constitutes a factor in this context are not clear from this single line of code. The resulting list of factors is stored in the variable all_factors. This code likely forms part of a larger program where universe is expected to be an iterable of names, such as strings, that are meaningful to the factors_from_names function. And the outcome of this operation is to prepare or retrieve a collection of data associated with those names for further use within the program. The code defines a function named setdiff that takes two lists, temp1 and temp2, as arguments. The purpose of this function is to compute the set difference between the two lists, meaning that it returns a new list temp3 that contains all the elements that are present in temp1 but not in temp2. To accomplish this efficiently, the code converts temp2 into a set S, which allows for fast membership tests, checking whether an element is in a set or not. Then it uses a list comprehension to create temp3 by including only those elements X from temp1 that are not present in set S. The resulting list temp3 is then returned. This operation is similar to subtracting one set from another in mathematics. This line of code involves three variables: risk_factors, all_factors, and alpha_factors. It is using a function called setdiff, which likely stands for set difference. Set difference is an operation that takes two sets and returns the elements that are in the first set but not in the second. In this context, all_factors is assumed to be a set-like collection that contains various factors. These could be financial factors, risk factors, etc., depending on the broader context. The alpha_factors is another set-like collection that contains a subset of factors also potentially present in all_factors. The purpose of the code is to assign to the variable risk_factors the set of elements that are present in all_factors but are not present in alpha_factors. In other words, risk_factors will contain all the factors that are considered risk factors but not alpha factors, with alpha presumably referring to some specific type or category of factors within the broader set. This operation will exclude any factors that overlap between all underscore factors and alpha underscore factors from the resulting risk underscore factors variable. The purpose of this line of code is to assign a value from a dictionary to the variable h0. The dictionary is referenced by the variable universe, and the code is accessing the value stored at the key h.opt previous. After the execution of this line, h0 will hold whatever value was associated with the h.opt previous key in the universe dictionary. If the key does not exist in the dictionary, this line would raise a key error. It is important to note that the context in which this line is executed is not provided, so the specifics of what universe is, what h.opt previous represents, and the implications of this assignment for h0 cannot be determined from this line alone. This line of code appears to be a function call to get underscore formula, passing two arguments, risk underscore factors and the string spec risk. The purpose of the function call is to retrieve a formula or computation that is associated with specific risk, presumably within some financial, statistical, or similar context. The exact nature or complexity of this formula is not clear from this snippet alone, but it's conceivable that get underscore formula is designed to select or generate a formula based on the provided input arguments. The variable formula is then assigned the result of get underscore formula, which implies that get underscore formula is expected to return a value that can be used later in the code. This value possibly represents a calculation or evaluation rule which takes into account the risk factors provided to make a specific assessment or operation regarding spec risk. The purpose of this code is to construct a design matrix for the predictors, independent variables, from a given dataset based on a specified formula. The patsy.matrices function is used to create two matrices, one for the outcome, dependent variable, and one for the predictors, from the input formula and data. The formula typically specifies the relationship between the outcome and predictors in a regression model, using a syntax similar to RS formula interface. However, this function only returns the matrix of predictors, ignoring the outcome matrix. This predictors matrix can then be used in statistical modeling or machine learning algorithms that require the data to be in a structured array format. The given code is performing matrix operations within the context of a statistical model, likely a linear regression or similar type. The equals model underscore matrix formula universe suggests that a model matrix B is being generated based on some formula and universe data. The formula would specify the relationship between variables, e.g., yx1 plus x2, and the universe would contain the actual data values for these variables. The function model underscore matrix would then create a matrix where each row corresponds to an observation, and each column corresponds to a variable or a transformation of a variable specified by the formula. This matrix is necessary for the estimation of model parameters. BT equals B.transpose indicates that BT is the transpose of the model matrix B. The transpose of a matrix swaps its rows with columns. Transposing is a common operation in the optimization algorithms of linear algebra, used either for fitting statistical models, where you might multiply a matrix by its transpose as part of solving the normal equations in linear regression, or for transforming the data for further analysis. The code snippet is performing a slicing operation on the spec risk column of a data frame named universe. Specifically, it is retrieving the first two elements, rows, from the spec risk column. In Python, indexing starts at 0, so the slice 0:2 denotes the elements at index 0 and index 1. The result of this operation will be a series containing the spec risk values for the first two rows of the universe data frame. The code snippet provided appears to calculate a new variable, specvar, based on the values found in the column spec risk of the data structure universe. Spec risk may represent the specific risk values for different assets or entities within universe. The calculation takes each value from spec risk, multiplies it by 0.01, which could represent a conversion from percentage to a decimal format, and then squares the result. The outcome is the specific variance for each asset or entity, and this is stored in the variable specvar. The specific variance is often used in finance to quantify the risk of individual assets that is not due to the market or sector risks, and the squaring operation emphasizes the impact of larger risks. This code snippet is accessing and manipulating a data structure, most likely a pandas data frame in Python, that is defined with the variable name covariance. It is attempting to retrieve the portion of data that corresponds to the index 200400102, which appears to be a date in the format YYYYMDD. The head function further refines the result by limiting the output to the first few rows of the resultant subset of the data frame. By default, it returns the first 5 rows. The purpose of this code is to quickly inspect the first few rows of the covariance data for a specific date, which could be part of a larger analysis or data processing task. This can be a common operation when dealing with time series data, where an analyst might want to examine or verify the data at a specific time point. Without more context, it's impossible to know what the covariance data frame represents precisely, but given the name, it could contain some form of covariance metrics or computations, which are useful in statistics and finance to understand the relationship between different variables or returns on different assets. The Python function callnames takes a single argument b and returns the column names of b if b is either a patsy.design_info.design matrix or a pandas.core.frame.dataframe. The function checks the type of b, and if it is an instance of design matrix, it accesses its design_info attribute to retrieve the column_names. If b is an instance of a pandas data frame, it calls the toList method on the data frame's columns attribute to get the list of column names. If b is neither of these types, the function returns none. This would be useful in situations where the column names are required for further processing, and the function provides a generic way to handle different types of objects that represent tabular data. The provided code is a Python function named diagonal_factor_cov that takes two parameters, a date string and a matrix b, and returns a square factor covariance matrix, fm. The function assumes there is a previously defined object covariance which contains covariances between factors, indexed by dates. The matrix B represents risk factors and could be provided in the form of a Patsy design matrix or a pandas data frame. The function extracts the number of factors k as the second dimension of the input b. It then initializes a square zeros matrix fm with a size of kxk. The code iterates over the range 0, k, and for each index j, it retrieves the name of the jth column factor from b. With this name, it looks up the variance from the covariance object for that particular factor and date, where the factor matches both factor 1 and factor 2 columns, indicating it is a diagonal element, and thus, variance rather than covariance. It corrects the unit by using 0.01**2 to convert the variance from percentage units squared to a decimal format and stores this variance in the jth diagonal position of the matrix fm. Ultimately, the code produces a diagonal matrix with variances of individual factors on the diagonal and zeros elsewhere. This matrix can be used in financial analysis to represent the standalone risks of each factor without accounting for the interactions covariances between different factors. The last line of the code snippet calls the diagonal_factor_cov function with arguments date and b and stores the result in a variable far. The purpose of this code is to define and use a function named get_lambda which operates on a data frame named universe. The function takes an optional argument composite_volume_column which has a default value of ADECA_30. Inside the function get_lambda, first, it addresses missing or NaN values in the specified column of the data frame by assigning a default value of 1.0 times 10 to the power of 4 10,000 to them. Next, it replaces any zeros in the same column with this same default value of 10,000. This could be to avoid division by zero or to standardize the minimal volume level across the dataset. Then, it retrieves the entire ADECA_30 column, or whichever is specified by composite_volume_column, and stores it in the variable ADV. After that, it calculates a transformation by taking 0.1 and dividing it by each element in the ADV series. The result of this calculation is returned as the output of the function. Finally, the function is called with universe as the argument, and the result is stored in the lambda variable. The result, contained in lambda, would be a series of values representing the calculated transformation applied to the ADECA_30 column or the column specified when calling the function. This transformation is likely used later for data normalization or scaling in a larger analysis or data processing workflow. This snippet of Python code defines a function named get_b_alpha, which takes two arguments, alpha_factors and universe. The function appears to be an incomplete wrapper for generating a model matrix, typically used in a statistical model or risk model context. The intended operation seems to involve creating a matrix b_alpha based on a formula derived from alpha_factors in the context of universe, which likely represents a dataset or a set of assets. However, the code is improperly formatted and includes a comment that disrupts the function definition. The line b_alpha equals get_b_alpha, alpha_factors, universe, outside of the function appears to be a call to the get_b_alpha function, which should return the b_alpha matrix once the function is correctly implemented. But as it stands, the actual implementation, the logic to compute b_alpha, is missing from the function body and only a comment placeholder is present with the word done followed by the intended logic. This call would store the returned matrix in a variable b_alpha that could be used elsewhere in the code. For the function to be functional, the commented placeholder needs to be replaced with the actual code that computes b_alpha, and the function body must be corrected syntactically. The purpose of this code is to define and use a function named get_alpha_vec that takes a matrix b_alpha as an input. The matrix b_alpha is expected to be an instance of patsy.design_info.design matrix, which is a specific type of matrix used in statistical modeling, commonly with the Patsy library in Python. The function creates and returns an alpha vector by performing a specific operation on the input matrix. This operation involves scaling the sum of each row's elements in the input matrix b_alpha by a factor of 1 times 10 to the power of -4, or 0.0001. The sum operation reduces the two-dimensional input matrix along its rows into a one-dimensional array. Each element of this array corresponds to the sum of elements in a row of the original matrix. This result is then multiplied element-wise by the scaling factor to produce the output alpha_vec, which is also expected to be in the form of a patsy.design_info.design matrix. After the get_alpha_vec function definition, the function is called with b_alpha as an argument, and its result is assigned to the variable alpha_vec. In essence, this part of the code serves to transform the input matrix into a scaled vector, where the scaling is a form of normalization or adjustment as specified by the variable scale. The provided code snippet is defining a Python function get_obj_func that constructs and returns another function obj_func. This inner function obj_func calculates the value of a specific objective function given an input vector h. The outer function requires parameters, such as the initial portfolio weights h0, a risk aversion coefficient risk_aversion, a covariance matrix Q, an array of specific variances spec_var, expected return vector alpha_vec, and a regularization parameter lambda. The purpose of the obj_func is to evaluate the trade-off between portfolio risk and expected return, where the risk is a quadratic function of the weights h with respect to the covariance matrix Q and specific variances spec_var, and the expected return is linear with respect to assets expected returns alpha_vec. Additionally, it includes a regularization term that penalizes the squared differences between the new portfolio weights h and the initial weights h0, weighted by lambda. The factors of 0.5 before the risk terms are standard in quadratic optimization, often to simplify the derivatives. In summary, the code sets up a function that, when called with a certain portfolio weight vector h, will calculate the expected risk-adjusted return of the portfolio, taking into account both the covariance of assets and their specific risks, and also encouraging solutions close to the initial portfolio through a regularization term. This kind of function is typically used in financial optimization problems to find the optimal portfolio that maximizes expected return for a given level of risk. The provided code defines a Python function called get_grad_func that returns another function defined within it called grad_func. Essentially, get_grad_func is a higher-order function that, upon being called with certain parameters, returns a closure that captures the provided arguments in its environment. The grad_func computes the gradient of a specific objective function often found in financial optimizations, such as mean variance optimization. The objective likely aims to find an optimal holding age that balances between portfolio risk, measured by risk_aversion, Q, QD, and spec_var, and returns, measured by alpha_vec, while also considering the difference from a target portfolio H0 penalized by a regularization parameter lambda. The formula for the gradient G involves matrix multiplication with Q and its transpose QD, element-wise multiplication with the specific variance spec_var, and subtraction of the expected returns vector alpha_vec. It also has a regularization term that penalizes the difference from the initial holdings H0, scaled by 2 * lambda. Once instantiated, grad_func accepts a single argument h, presumably a vector representing current holdings in a portfolio, and computes this gradient based on the captured parameters. The result is a vector, and p.asArray G ensures the result is returned as a number py array, which can be used in optimization routines to iteratively adjust h towards an optimal portfolio. The Python code defines a function get_h_star that is used to compute an optimized set of holdings h_star based on a given objective function. To achieve optimization, the code makes use of the fmin_l_bfgs_b function from the sipi.optimize library, which is a popular algorithm for optimization of functions with linear constraints. The get_h_star function attempts to find the set of holdings that maximizes an investor's alpha expected return in excess of the risk-free rate, while considering a trade-off with risk, as indicated by the risk_aversion parameter. It takes in several arguments including risk_aversion, a parameter that indicates the trader's potential to tolerate risk. Question A matrix formed by the multiplication of the square root of a factor covariance matrix var in the transpose of a factor loading matrix bt. QD, the transpose of the Q matrix. Spec_var, specific variances associated with the assets. Alpha_vec, expected returns alphas of the assets. H0, initial holdings before optimization. Lambda, a series containing lambda, which seems to be a parameter related to transaction costs or constraints in the optimization problem. The get_h_star function sets up an objective function, obj_func, and its gradient, grad_func, that are used by the optimization algorithm. These functions likely calculate the expected return adjusted for risk and possibly other constraints or transaction costs. fmin_l_bfgs_b is then called with the initial holdings h0, the objective function, and its gradient to find the optimized holdings. The result of the optimization, optimizer_result, is returned, particularly the first element of the tuple which contains the optimal holdings h_star. Finally, h_star is obtained by calling get_h_star with the relevant parameters. This optimal set of holdings represents the portfolio positions that the algorithm determined best for the given inputs, according to the model's risk-return profile and possibly transaction costs or other constraints. The given line of code creates a new pandas data frame named opt_portfolio. This data frame has two columns, borrowed and h.opt. The borrowed column is created by extracting the borrowed column from a pre-existing data frame named universe. The h.opt column is created by taking the variable h_star, which could be an array, series, or list that matches the length of universe, borrowed. The purpose of the code is to pair each borrowed value with a corresponding h.opt value, essentially forming a portfolio that indicates an optimal holding h.opt for each identifier, borrowed. This could be part of a financial application where borrowed represents unique identifiers for financial assets, like securities, and h.opt represents the optimal holding quantities or weights for these assets in a portfolio. The code snippet defines a Python function named get_risk_exposures that calculates the risk exposures of a portfolio given a matrix of risk factors, the transpose of that matrix, and a vector of optimized holdings. The function expects three parameters, b which is the matrix of risk factors, bt which is the transpose of the matrix of risk factors, and h_star which is a number py array containing the optimized holdings. Inside the function, the numpy_matmul function is used to perform matrix multiplication between bt, the transpose of the risk factors matrix, and h_star. This operation calculates the risk exposures for the portfolio. The result of the multiplication is then converted into a pandas series, with the index set to the column names of the B matrix, which presumably represent the names of the risk factors. Finally, the function returns the pandas series of risk exposures. At the bottom, the function is called with inputs b, bt, and h_star to compute the risk exposures, which are presumably stored in the variable risk_exposures. This code defines a Python function named get_portfolio_alpha_exposure that calculates the alpha exposures of a portfolio. The function takes two arguments, b_alpha, which is expected to be a matrix of alpha factors represented by a Patsy design matrix, and h_star, which is a numpy array of optimized holdings. The computation involves taking the matrix b_alpha, transposing it, and then multiplying it by the vector h_star using matrix multiplication and b.matmul. The result of this operation is a set of alpha exposures for the portfolio. Finally, the function returns these alpha exposures as a pandas series, with the series index set to the column names of the alpha factor matrix b_alpha, although the code for retrieving call names, b_alpha, needs to be implemented. At the end of the snippet, the function is called with the variables b_alpha and h_star to obtain the portfolio alpha exposure. However, the assignment to portfolio_alpha_exposure variable suggests that this line is not part of the function definition, but rather its application in some other part of the code. The provided code defines a Python function get_total_transaction_costs that calculates the total transaction costs based on initial holdings, before optimization, optimized holdings, and a parameter lambda. It expects three arguments, h0, a pandas series representing initial holdings, h_star, a number py array representing optimized holdings after optimization, and lambda, a pandas series representing a cost coefficient. The function computes the squared differences between the optimized holdings h_star and the initial holdings h0, element-wise. These squared differences are then element-wise multiplied by the corresponding values in lambda using the dot product. The sum of the result of this operation is considered to be the total transaction costs, which is finally returned as a float. After the function definition, the code calls this function with actual parameters h0, h_star, and lambda to calculate and store the total transaction cost in the variable total_transaction_costs. This code defines a function named form_optimal_portfolio that takes as input a data frame df, a data frame previous, and a parameter risk_version. The function merges the input data frame df with historical data previous on a unique identifier borrowed, cleans any NaN values, and performs calculations to form an optimal financial portfolio based on the merged data. The code calculates specific and factor risk measures, constructs a model matrix B from risk factors with a separate handling for alpha factors, sources of investment returns independent of market movement, and computes the risk exposures using these matrices. It handles specific risk by setting any zero values to the median specific risk. The variable lambda likely holds transaction cost data or a risk aversion measure to penalize deviations from the previous holdings h0. The alpha_vec represents the expected returns vector, and the calculation of the new optimal holdings h_star is influenced by the existing portfolio h0, the risk_version coefficient. The risk model components such as Q and QD, which are related to the factor covariance matrix var, and specific risk spec var. Finally, the function calculates and returns an optimal portfolio opt_portfolio with the holdings h.opt, the associated risk exposures for the portfolio, the alpha exposures. portfolio exposure to returns from alpha factors, and the total transaction costs incurred from rebalancing the portfolio to the new optimal holdings H_star. This code defines a function build_tradilist that takes two arguments, prev_holdings and opt_result. The purpose of the function is to merge two data frames, namely prev_holdings and the data frame contained within opt_result, opt portfolio, on a common column called bar_it. The merge is done using an outer join, meaning that the result will include all rows from both data frames, with matching rows from both sides where available and nans for non-matching rows. After merging the data frames, the function replaces any nan values that may exist in the columns h.opt previous and h.opt with zeros. This is done using the imp.nan_to_number function from the number.py library, which converts nan values to 0. The modified data frame TMP, which now has zeroed nans and contains combined information from both the previous holdings and the optimized portfolio, is then returned. The function is likely used in the context of financial portfolio optimization to align the current portfolio with a newly optimized portfolio and prepare a list of trades that need to be executed to transition from the current to the optimized holdings. The purpose of this code is to create a modified copy of a given data frame, which is an object containing structured data similar to a spreadsheet or SQL table, typically provided by the pandas library in Python. The function convert_to_previous takes a dictionary result as input, from which it extracts a data frame under the key opt portfolio. It then creates a new data frame by renaming a column in this original data frame from h.opt to h.opt previous. The rename method is set not to modify the original data frame, in place equals false, but to return a new data frame with the changes. Finally, this new renamed data frame is returned by the function. This code allows users to easily reference an historical or previous state of data by renaming the relevant column, presumably to compare it with current or updated data. This code snippet seems to be part of a larger program related to financial portfolio optimization. Specifically, the code is iterating through a series of dates referred to as my_dates while optimizing a portfolio for each date. For each date, dt, in the my_dates list, 1. The date is formatted as a string date in the format YYYMDD. 2. An optimal portfolio is formed for the given date by calling form_optimal_portfolio with parameters that typically include the market data or price frames for that date, the previous holdings of the portfolio, and some measure of risk aversion that the function uses to balance return versus risk. 3. The build_tradilist function generates a list of trades that must be executed to transition from the previous holdings to the newly formed optimal portfolio. The resulting trades for that date are stored in the trades dictionary. 4. The port dictionary is updated with the newly calculated optimal portfolio for the date. 5. The variable previous_holdings is updated to reflect the current holdings for use in the next iteration. This is likely achieved by converting the current optimal portfolio result into the format expected by the next iteration as previous holdings. During the loop, a progress bar is displayed in the console thanks to the TQDM module, indicating optimizing portfolio and tracking progress by day. By the end of the loop, trades will contain all the necessary trades to be made for each date to achieve an optimal portfolio as per the defined algorithm, and port will contain the composition of the optimal portfolio for each day. This code defines two functions, partial_dot_product and build_P&L_attribution, that appear to work together for financial data analysis, more specifically for calculating a profit and loss P&L attribution of a trading portfolio over a sequence of dates. The partial_dot_product function calculates the dot product of two pandas series only for items that have matching indices. It first finds the common indices of both series, then multiplies the corresponding elements and sums up the result to get a scalar value. The build_P&L_attribution function creates a new pandas data frame, meant to store the results of P&L calculations on a set of dates contained in my_dates. For each date, it performs several calculations to attribute daily P&L to different factors, such as predicted alpha, risk exposures, and costs. Within the loop for each date, 1. It merges the portfolio, denoted by P, with another data frame, acquired from frames, date, based on a bar_it column. It seems that the portfolio information for that date is already stored in a dictionary-like structure with dates as keys, port, date, as well as factor returns, facret, date. 2. It applies a winsorization function, wins, to the daily return column of the merged data frame MF, which likely aims to limit the influence of extreme values. 3. It calculates the daily P&L by multiplying holdings, h.opt, by daily returns, daily return, and sums them up for the given date. 4. Then, the function aims to create separate attributions for the P&L, splitting it into alpha value derived from the model's predictions, risk, exposure to systematic risk factors, and cost associated with maintaining and rebalancing the portfolio. It calls partial_dot_product with the factor returns and respective exposures to calculate the alpha and risk P&L. Additionally, it directly assigns total.cost to the corresponding P&L attribution. 5. Once all the calculations are done for each date, the data frame DF is returned with daily P&L and its attributions for the whole period in my_dates. The to-do comment suggests that the function is not yet fully implemented, particularly the P&L attribution to alpha isn't done in this snippet. The code snippet aims to provide a granular understanding of what components are contributing to the daily P&L of a trading strategy or portfolio over time. This is commonly done to assess performance and understand the sources of return, be it from market movement, specific stock selection skill, alpha, or other factors. The purpose of this code is to generate a cumulative plot for the profit and loss P&L attribution of different components over a certain time period, which is likely represented by dates. Initially, it seems to call a function build_P&L_attribution, which constructs and returns some form of P&L attribution data, presumably in the form of a data frame, where each column represents a different component of the P&L attribution. For each column in this data frame, the code then plots the cumulative sum of that specific P&L component, creating a line graph. This would give the user a visual representation of how each component contributes to the overall P&L over time. The use of plt.legend, lock equals upper left, adds a legend to the plot, which helps to identify each component's line in the graph. Naming the x-axis as date with plt.label, date, implies that the index of the data frame likely corresponds to dates. Labeling the y-axis as P&L attribution with plt.label, P&L attribution, implies that the values being plotted are contributing factors to the P&L. Finally, plt.show displays the plot. Overall, this visualization would allow a user to easily discern trends and the impact of individual P&L components over the given time frame. This code defines a function named build_portfolio_characteristics that is intended to calculate and return a data frame containing various portfolio characteristics for different dates. The data frame df is indexed by a sequence of dates my_dates. For each date in my_dates, the function formats the date as yyyymmdd, retrieves the portfolio P and trades trade list for that date, and calculates various characteristics. Long_pus is the sum of positive holdings in the portfolio, representing the long positions. Short_pus is the sum of negative holdings, representing the short positions. Net is the net position, calculated as the sum of long and short positions. GMV is the gross market value, calculated as the sum of the absolute values of the long and short positions. Traded is the total traded amount, calculated as the sum of the absolute differences between the current and previous holdings. Each calculated characteristic is stored in the DF data frame under specific columns, long, short, net, GMV, and traded, at the index corresponding to the current date. After iterating through all dates and performing the calculations, the function returns the populated data frame df. The code assumes that all needed variables and libraries, like pandas as pd and numpy as np, are already defined and imported in the wider scope where this function is called. This code snippet is used for plotting the characteristics of a financial portfolio over time. It begins by calling a function build_portfolio_characteristics to retrieve the portfolio data, which presumably returns a data frame with different characteristics as columns where each characteristic is likely a time series. For each column in the return data frame, char, a line plot is created using plt.plot with the data from that column. This is done in a loop, iterating over each column in char. Each line in the plot is labeled with the name of the column corresponding to a specific portfolio characteristic, as the label parameter is set to the column's name. The plt.legend, lock equals upper left, line adds a legend to the plot, positioning it in the upper left corner. This legend will help distinguish between the different lines on the plot, denoting which line corresponds to which portfolio characteristic. Next, plt.label, date, and plt.label, portfolio, set the labels for the x-axis and y-axis of the plot, respectively, indicating that the x-axis represents dates and the y-axis represents the portfolio characteristics values. Finally, plt.show displays the resulting line plot with multiple series represented. This visualization allows the user to observe how the various characteristics of the portfolio change